So we're going to start chapter 5 with a couple theorems. One is called the extreme value theorem, but in order to have a theorem, you got to know what an extreme value is. So we're going to start with the definition of what an extreme value is. All right, so it kind of is broken up into a couple different categories. So if I say extreme values, in that category, I am including any endpoints. And the endpoints would be of a closed interval. So if you had the interval was not all real numbers, but the interval was starting at a particular A and ending at a particular B, those endpoints are part of what we would call extreme values. The other category, besides endpoints, are what are called critical points. And critical points are within the interval somewhere. And a critical point is when where the first derivative is either 0 or undefined. Where the first derivative is either 0 or undefined. Now, if a first derivative is 0, what does that mean the tangent is at that point? If a first derivative, which is the tangent, is 0, what does that mean? What kind of line? A horizontal line, okay? And so the horizontal line at that place is either sitting on a max or it's sitting on a min. Okay, it's either on a peak or it's on the bottom of a valley. And so the 0 is going to be maxes or mins. If the first derivative is undefined, now you're talking about corners or cusps or vertical tangents. Corners, cusps, vertical tangents. All of these things fall into the category of extreme values. So if you have an extreme value, I'm talking about all endpoints, and I'm talking about any max or min or corner or cusp or vertical tangent. Those are all considered extreme values. If they only say critical points, then you only have to focus on those couple. Okay, but those are the definition of extreme values. All right, so that leads us to the extreme value theorem. All right, the extreme value theorem, or the EVT. Oops. All of the theorems that we're going to learn this chapter apply to closed intervals. And so we have to assume a couple things. Assume a closed interval, and the closed interval would be going from A to B. So you have to be, on a closed interval, blank to blank. Not only do you have to have a closed interval, but you have to be able to assume both continuity and differentiability. And a more efficient way to do that, let me get this down here. Differentiability. Okay, assume those two things. Actually, you really only have to assume one of them. Okay, you really only have to assume which one? A differentiability, because if you've got differentiability, you've got continuity. They go hand in hand. You can't have differentiability without continuity. Now, they could say continuity and not have differentiability. Okay, I take it back. Just assume we don't need differentiability for this problem. We need that for the MVT, not the EVT. We just need continuity. That'll make it work. If you have a closed interval, and if you have continuity, The extreme value theorem says, okay, then we are guaranteed at least one max and one min on the interval, or within the interval is a better way to say it. And it could include the endpoints as well. All right, assuming a closed interval, assuming continuity, you're guaranteed that there has to be at least one highest value and there has to be at least one lowest value that's higher than all the others and lower than all the others. Okay, that is the extreme. Yeah?
If it were to be a horizontal line, would it just be the entire line as the maximum?
It's not a horizontal line, it's a horizontal tangent, which is invisible, and it's only a horizontal for that one moment where it's at its peak. All right, so I'm going to draw a pic. Sometimes having a picture helps us understand a little bit better. All right, we could have something that looked like this. All right, here we go. Okay, there is something that has a closed interval and it's continuous. Is it differentiable? Yes or no? Is it differentiable? Is it continuous?
Yes.
Is it differentiable?
No.
Why not?
They're close.
There are corners and a cusp. Okay. But it is continuous and it is closed. Therefore, the extreme value theorem says there has to be an extreme high, which is the max, and an extreme low. There are other things that we call relative maxes and mins. Okay, so if you look at this piece right here, there's a horizontal tangent, and here's another horizontal tangent, and then we've got corner, corner, and then we've got another horizontal tangent, and then we've got cusp. So we've got corners here. Okay, I've got a corner here and a corner there. And then I've got a cusp. Now there is a difference between relative maxes and absolute or extreme maxes. So we have several things that would be considered maxes, and we have several that would be considered mins. All right, this horizontal would be considered a max. So would this corner. So would that corner. Because they're pretty high within their own little domain, their own little area. But if you consider the entire interval, only one of them can qualify as the extreme or the absolute max. And then the same thing would be true for mins. We have a min here, and here, and here, and again here. Okay, we've got 4 what are considered relative mins. But of those 4, only one would be considered the absolute or the extreme. Unless they were perfectly tied. If they were perfectly like the exact same y value, then you can have a tied value for the extreme. Okay, but that doesn't happen very often. Oh, cusp is a max. So that's the visual picture. Now how do you do the math behind that? Okay, how do you do the math behind that? What you want to do is look at every time something's happening between between one of those values, either it's an endpoint or a critical point, you want to look at what the slope is doing on either side. So I'm going to look at this max here a minute. Assuming that it's right there, let's say just hypothetically that's the best I can do. Up until that green dot, what kind of slope is happening? Okay, and after the green dot, what kind of slope is happening? Okay, we call that a plus-minus change. Okay, it's changing from pluses to minuses, from positive slope to negative slope. Okay, let's look at this max up here. Okay, assuming that the max is happening at this corner right here. All right, what kind of slope is prior to it, like on the left-hand side? Positive slope, and then negative slope. That's another plus minus change. Okay, and then on the cusp, on one side we have positive slope, on the other side we have negative slope. So those all have that in common. Now there's one I want you to look at. Okay, what about that corner right there? What kind of slope does it have on the left side? Okay, what about after the corner, which is right here, what kind of slope does it have? Okay, so there's no change in that. It's positive in nature, and it's staying positive in nature. That has a special name. Okay, that is called a stationary point. Stationary, if something is stationary, it means it's not moving or not changing. And in that case, the slope is not changing nature. I know the slope is changing value, but it's not changing nature. It is not changing from positive to something non-positive. It is not changing nature, so we consider that a stationary point. Other than that, all of the maxes have the thing in common where they're changing from a plus to a minus. That is what identifies a max. Yeah? Stationary point, right. Okay, so then let's look at our different minimums. Okay, the minimum that's happening right here, okay, we'll assume that the minimum is happening at that dot. Prior to the minimum on the left side, what type of slope do we have? Negative. And then on the other side we have positive. That identifies a minimum. When it's changing, when the slope is changing from negative values to positive values. Same thing with this minimum here. Okay, that is changing from negative slope on this side to positive slope on the other. That is also considered a minimum. All right, what about at the ends here? Okay, so this minimum at the end, what type of slope does it have on the left-hand side as I'm coming down? Okay, what about on the right? Yeah, it does not exist. Okay, that is still considered a change, and so we still qualify that as a minimum. And then on the other side, okay, for that minimum, we have positive slope on this side, but no slope on the other. That's also considered a change, and it is considered a min. Yes?
So for the stationary point, the max, so would it not be identified as a maximum at all?
So it would be disqualified as a max, right? So I'm going to put a line through that. It is no longer considered a max. Okay, it is relabeled as a stationary point. In order to prove a max, you might think something might be a max or whatever. In order to prove it, you have to be able to cite a change in the nature of the slope on either side. And so as Bella pointed out, if we did come across a negative, that would also qualify under stationary point. Okay, this is all picture stuff. Okay, I want to actually do some math that goes with it. How are you guys feeling about the picture and understanding? Any other questions on that?
Is there any name for the endpoints of this? Like, because it has one type of slope on the right.
Not a special name. No, but I would identify this one as being absolute, the absolute minimum, because it is the lowest of all the minimums. And then I would identify this one up here as being the absolute max because it is the highest of all the maximums. It is the most extreme of all of the extreme points. All right, great. Josh, you with us back there? Okay. All right, so the math. All right, what are you going to have to do? This is sort of like a ooh, I don't like that. Okay, the math procedure. All right, first, you're going to find the derivative. Second, you're going to set the derivative can I write it as f prime? Save myself time. Set f prime equal to 0 and solve. And third, set f prime equal to 1 over 0 and solve. We need to set it equal to 0 to find any of our soft rounded points where I'm going to possibly have a max or a min. Why am I setting it equal to 1 over 0?
So we can find the cusp.
Corners, cusps, vertical tangents. All right, once you have all of those, those are called the critical points, right? That group of things right there, those are called the critical points. And then the fourth thing is to test all endpoints and critical points for slope change. And when I'm talking about slope change, I'm talking about plus, minus, minus, plus, etc. Or maybe no change at all. And I'm going to show you a nice mathematical way to do that. That's the procedure. So we're going to do that for, I've got five questions for us to try that on. Okay, that's the overall procedure. Find the derivative. Find all the critical points. Assuming you're on a closed interval and this is continuous, then we're going to test all of them for their slope change. All right, so let me show you how that works. Let us start with the following function. It's a cubic, x to the third, minus 75x plus 100, and we're going to be working on the closed interval 0 to 6.
The 0 to 6 are endpoints.
Yep, the 0 to 6 are your endpoints. Okay, so our procedure is find the derivative. We have our endpoints. We have to find our critical points by setting the derivative both equal to 0 and undefined. And then I'm going to show you how to test those for any kind of change. All right, so let's find our derivative, f prime. We've got 3x squared minus 75. I'm going to set that both equal to 0 and undefined. So I'm going to take that f prime of x and solve it twice. I'm going to set it equal to 1 over 0, and I'm going to set it equal to 0. That's just straight math. That's just straight algebra. Of course, we can factor. When we factor this, we'll have 3 times x minus 5 and x plus 5. When I set it equal to 1 over 0, you're going to drop a 1 under your function so you can cross multiply. You're going to get 0 equals 1, which is not true. So there are no corners or cusps or vertical tangents, but the critical points I come up with are 5 and negative 5. All right, so we took our derivative, we set the math equal to 0 and 1 over 0. We found that there are no, hey Joanne, maybe not, let me save it for later. There are no corners, cusps, or vertical tangents, but there are 2 places where we've got maxes or min dips going on with 5 and negative 5. Of course, one of those is not even in the interval I'm looking at. Okay? So this is how now you're going to set up the test. We want to test them for plus and minuses. We are going to start at the beginning of our interval. The beginning of our interval is starting where? 0. So you're going to set it up like this. 0 up until the critical point of 5. Okay, 5 is considered a critical point. Then I'll pick up at 5, and I'm going to go up until the end point of 6.
So we also have to do negative.
We don't, because our interval starts at 0. We're not concerned with negative 5, because for this time it didn't fall into my interval. If my interval had included, say my interval was negative 6 to positive 6, then for sure I would have had to include it. Okay, and so you make sort of a little chart right here, and we're going to test the values of the slope. And we're going to pick arbitrary values within that interval. It works for any value between 0 and 5, just not 0 or 5 itself. Okay, so pick me a number that's between 0 and 5. 1. Put it into the derivative. Just mathematically in your head. You don't have to tell me what you get. Just tell me what the nature is going to be of what you would get. You're going to get a negative number, so you just put a negative right there. Okay, and that would work for any arbitrary value between 0 and 5. All right, pick me an arbitrary value between 5 and 6. 5.5, okay? Put that into the derivative, and you do not have to compute the exact value. You just have to know if it's going to turn out to be a positive or a negative number. So when you're plugging in 5.5 into that value, you think, well, it's more than 5. If I plugged in 5, I'd get 25. I'm plugging in 5.5. So I'm going to get more than 25. Multiply it by 3, I'll have more than 75. And so when I subtract 75, I will have what kind of number? Positive. And because you now have identified it as being a minus to plus, what does that mean is happening at the number 5 itself? What kind of critical value is it? It is a minimum, because the slope is changing from a slope that's decreasing, then changing to a slope that's increasing. So we have just achieved a minimum. So we now know that there's the extreme value, there's a minimum at x is 5, because if I ask you why, you got to be able to tell me in a complete sentence, because the slope changes from decreasing to increasing. Okay, that's a pretty simple sentence that will buy you full points on an FRQ or something when you have to defend it. Tell me if it's a max or min and tell me why, how you knew. We also need to check our endpoints to find out which one of them is the max. So we want to actually check the values of 0 and 6 in our actual equation. So now we're going to check our endpoints. F of 0 and f of 6 themselves. Clearly, if I plug 0 into the function, what do I get? And then you might need your calculator to figure out what you get for, I don't know, it depends on how good you are at mental math. We've got 6 to the third, that's 216, minus 75 times 6, so let's see, that's 450 plus 100. Anybody got that answer? Original equation, right, because we want the y values of the original. I don't know, somebody got a calculator. 216 minus 350, so negative 134. So clearly, f of 0 is the absolute max. What does that mean negative 134 is? No, it's not a min at all. It's not a min at all. Okay, why? Okay, think about what this graph is doing. Okay, at 0, it's starting at 100, and then according to the negative, what direction is it going? It's going down. And then when I get to the number 5, I'm going to turn around, and I'm going to start going up. I don't go up very far, but I do go up. And so this one is your absolute max, but we've turned the corner. And so at 6, what do we have? A relative max. Okay, you got to think about what's happening. This function is doing this, and then coming back up again. It doesn't go up very high, right? This one is 100, and this is negative 134. But guess what? Your min is lower than that. That's the absolute min. We've got an absolute min going on here. We've got the absolute max at 100. But the endpoint of negative 134 is a relative max, not a minimum. Just because it's negative does not mean that it's a minimum. It is a relative. It's maximum and it's relative. Because it's going back up. Right. So it is higher. You just think, is it higher than the point before it? Yes, it's higher than the point before it, therefore it's a max. Okay, let's try another one. Let's try the following example. How about f of x equals x to the 2/3, and we're going to go on the interval from -2 to +3. Oops. So we're going to find our derivative. We're going to look for the critical points of our derivative, which come from 0 and undefined values, and then see what we've got. So our derivative f prime is 2/3 times x to the -1/3. So that is 2/3 times the cube root of x. All right, 2/3 times the cube root of x. I will be setting that derivative equal to 0. I will also be setting it equal to 1/0. So I'm going to set that equal to 0 or 0/1, and the other one equal to 1/0. Both options in the math, I'm going to cross multiply. When I cross multiply, I get 2 equals 0, which is not true. So there are no soft, rounded max or mins. Hopefully I come up with some corners or cusps. When I cross multiply here, I'll end up with 3 cube root x equals 0. Okay, right. So x does equal 0. So I've got a corner or a cusp or something going on at x equals 0. So now I want to test my endpoints along with my critical point that I just found. Okay, so remember, you've got endpoints given. These are your critical points. So you set up an interval starting at your endpoints, so -2 up until the critical point we found, and 0 up until the other endpoint. And we're going to check derivative values. So pick a number between -2 and 0 and plug it into the derivative. -1, sure. When you plug that into the derivative, it doesn't matter what you get, just the nature. So if you're plugging a negative number into the derivative, what do you get? You get a negative number. So if you pick -1, what's the cube root of -1? Still -1. Okay, you can cube root a negative number. And so that's going to be negative. And then pick a number that's between 0 and 3. 1 is easy. Plug that into the derivative, because we're only checking the derivative values here. That turns out to be positive. So once again, what kind of value am I ending up with? Okay, I'm ending up with a min again. So here's another way to kind of check your y values. I'm going to need 3 y values. Sometimes people do it like this. Just check the y value at -2, check the y value at 0, and check the y value at 3, and that goes back to the original function. Okay, you're going to plug the original function back in. And so the original would be -2 to the 2/3, 0 to the 2/3, and 3 to the 2/3. Go ahead and use your calculator. What do you get with -2 to the 2/3? I'd love a decimal value from somebody.
The cubic root of,
Okay, I'd love a decimal value.
that would be 1.5.
1 point how much? Okay, somebody else. I'd love some cube root of 4, cube root of 9.
-1.
I can't have a negative. There's no way I could possibly get a negative. Say it again.
1.587.
587. Okay, there's no way to possibly get a negative, especially if you're using parentheses, because -2 to the second is +4. right, and then this one clearly would be 0. All right, how about the other one?
2.08.
Okay. All right, so now we can clearly tell which one is the absolute max and which one is the relative max. And this one had to be a min. Okay, and that is the min absolute. We know it's the min absolute because we're changing from minus to plus. We can defend it because the slope is changing from decreasing to increasing. It has to be a minimum. It's a decreasing slope to an increasing slope. This one is going to be your absolute max because its y value is the highest, which means this one has to be a relative max. Okay, just keep in mind that you can't have like 2 maxes in a row. It's got to go max, min, max, or stationary point. You can't have more, you can't have them, you can't have 2 maxes next to each other or 2 mins next to each other in order. Okay, how are you guys feeling so far? Okay, yeah.
Is this all they're gonna ask us for, like, in the problems, or what are they gonna ask us to get on this?
They may, well, I'm doing everything right now. They just may pull out like one thing at a time, tell me, but we're doing it all. Yeah, this would be like, an FRQ, it'd be asking you to do, find this, and put it all together. So we're kind of doing everything at once. Okay, let's try this one. Let's do the function 1 over the square root of 4 minus x squared. What have I not given you? Okay, but there are endpoints because this function is defined on a closed domain. What numbers am I allowed to only use? I can't use anything that would make the square root negative. So what am I bounded between? Not negative 4. If I use negative 4, I'm going to get 4 minus 16. That won't work. But negative 2 to 2. Okay, I'm bounded then on negative 2 to 2. So sometimes they're not going to give you the interval. You have to know the boundedness of the domain and come up with your interval on your own. So then we would set up f prime, and we would take a look at that. Okay, I don't want to use the quotient rule. So I'm going to go ahead and rewrite this function. Instead of 1 over the square root, I'm going to write it as 4 minus x squared to the negative half. To me, that's a much more preferred way to write that. So that'll give me negative half as my derivative, 4 minus x squared to the negative 3 halves times the chain rule of negative 2x. So when I clean that up, my negative 1/2 will reduce my negative 2, but I still have x in the numerator, and I have 4 minus x squared to the positive 3 halves in the denominator. I am going to take that, and I'm going to set it equal to both 0 over 1 and 1 over 0. So I'll do that twice. I'm going to set it equal to 0 over 1 mathematically, and I'll set it equal to 1 over 0. And both times now I'll cross multiply and see what critical points we end up with. The first time when I cross multiply, I get x equals 0. So there's my first critical point. The second time when I cross multiply, I get 4 minus x squared to the 3 halves equals 0, which gives me the values of plus and minus 2, which I actually already had as endpoints. So I've got my sets of critical points, so I'm going to set up from the interval between negative 2 and 0, and then the 0 up until positive 2, and I will be checking first derivative values, and I'll also be checking y values. So I'll get my y values from that, and I'll get my slope values. Okay, pick me a number between -2 and 0. -1, plug it into the first derivative. What do we get? Another negative number. You're going to think all of them turn out to be negative first. And then if you plug in +1 into the first derivative, you're going to get a positive number. So once again, we have identified a minimum because it's changing from positive to negative. Then you check the y values, and you plug the y values in. What if, okay, I'm going to pause there because I know you can plug numbers in and find y values. I just brought up something hypothetically for you. What if you ended up coming up with this? What if you were given this table, because sometimes they'll give you the table and ask you to work from it. What if you have from -3 to -1, and then from 1 up to 2, and then 2 up to 5? So really this interval starts at -3 and ends at 5. And what if it comes up like this? All right, how would you interpret then that table? All right, so tell me what's oops, I forgot negative, sorry about that. What's happening at -1? What kind of change is there happening? It's changing, and use words like increasing, decreasing, whatever. Okay? This means increasing. This means decreasing. So if it is changing from an increasing graph to a decreasing graph, what's happening at -1? Okay, it is a max. We've identified that. Okay, then if it's decreasing and decreasing again, what's happening at 2? Stationary point. Okay, very good. And if you had to defend it, you should be able to write a sentence. Okay, the maximum would be, we're having a max because it's changing from, the slope is changing from increasing to decreasing. Okay, and then the other one, we are having a stationary point because the nature of the slope, the function is decreasing and continuing to decrease. There's no change in the direction of the graph.